Before we start? Okay, so today we're going to talk about the Pontragon Tom Construction. Last time I started give an introduction to the definitions, but today I'm going to start again and go a little slowly, a little slower. So Pontragon Tom Construction. So as I said, this is a generalization of the Hopf degree theorem. So this is a way to classify maps from compact connected oriented manifolds into Sn. Actually, they don't have to be connected. Yeah. So this is a way to classify maps into Sn, but where n could be greater than n, up to homotopy. Okay, so last time I talked about what it means for a submanifold to be framed and what a cobordism was, but I think I'll do that again because it's a very important thing and I don't want anybody to be lost. So let's take X in oriented manifold without boundary. And let's consider a submanifold of X, which is also oriented. And yeah, that's enough, actually. And no boundary. So we can define what it means for the manifold to be framed. So if the normal bundle is trivial, so if this is trivial, meaning that it's isomorphic as a normal bundle to Q times R to some power. I mean, if let's say X has dimension n and Q has dimension k, so this will be n minus k, then a framing is a choice of such an isomorphism. Okay, so if you're given one of them, then you can always find many different ones. Like for example, if you have a loop in Q, you can use that loop to rotate your bases. For example, there are many different ways they can change. But if you have one, then you will have many. And usually you'll have many even up to isotopic classes. Okay, but anyway, so yeah, another way of choosing one way to choose a framing is to say I'm gonna choose n minus k, a basis of the normal space at every point in a way that's smooth. So an equivalent way, an equivalent definition is the following. So you can look at the normal bundle and you can look at sort of the induced, I don't know, I'm going to call it like this. B of NQ, maybe that's not the best. V of NQ. V of NQ. So this is the union of Vx of NXQ, or V of NXQ for X in Q. And V of NXQ is the choice of, this is a set of pairs, V1 through Vn minus Q, such that V1 through Vn minus Q is a basis of NXQ. And a framing, and we can check that this is a bundle, is a fiber bundle in a framing is a section of this bundle. So okay. All right, so that means that for every point in Q, I choose a basis of the normal space above that point in a way that this varies smoothly. So that's kind of what's encoded in the definition of a smooth section. Okay, so any questions about this, what a framing is? I gave some examples last time for knots. Okay. And again, what I guess I could say one more time what the normal bundle is. And the easiest way to define the normal bundle is really as a sub-bundle of the tangent bundle of X restricted to Q. So that's not very canonical, but it doesn't matter. Up to like some clear isomorphisms. But in general, I'm going to be thinking. So we usually think that there is a Riemannian metric on X, or we think that there is a given Riemannian metric on X for which we can take orthogonal complements. So that really we think of the normal bundle as being the orthogonal complement of the tangent bundle, which is just a subbundle of Tx. If you don't choose a Riemannian metric, if you just want to define the normal bundle in general, you can do that. And actually, the existence of these things doesn't actually depend on choosing a Riemannian metric at all. But then you will not have a subbundle of Tx in a canonical way. But actually, for the up to isotopy, it's kind of you don't really have to worry about choosing a Riemannian metric. But anyway, we can just imagine that we always have a base Riemannian metric to do things with. Okay. And finally, I want to say that sort of if we suppose that Q is oriented, if Q is oriented, then we will only look at oriented framings. So if Q is oriented, then we kind of assume that almost if we don't say anything, then we mean that the framing is oriented. Then we usually assume that the framing is positive. Is positive with respect to the orientation. Yeah, so what does that mean? So if the manifold is oriented, then the normal bundle has an induced orientation. That's induced, by the fact that Txq plus Nxq is equal to Txx for x and q. So if these two are oriented, then there is a natural notion of orientation on Q. So a given framing can be positive or negative. If, when you put the framing here and the unoriented frame, a positive framing here, a positive basis here, we get a positive basis here. Okay, so this is the usual orientability condition. Okay? So, if we have an oriented manifold, which we will have in just a moment, and I say you consider a framing, I'm automatically assuming that it's an oriented, it's a positive framing. Okay? So, because I don't want to keep saying that. Okay. All right, so now let's recall what cobordism is. I'm actually going to change the definition slightly, and you'll see why, to make things a little bit easier later on. So now, if I have Q0 and Q1, compact and oriented submanifolds, without boundary, so I'm going to define what a cobordism from one to the other is. So a cobordism from Q0 to Q1 is an oriented compact manifold W inside of 0, 1 times x. And last time I assumed that this manifold was basically the boundary of that was Q0 in 0 times x and Q1 in 1 times x. But I'm going to suppose something a little bit stronger. So I'm going to suppose the following, such that, so I want this guy, the intersection of this guy with 0 epsilon union epsilon 1 minus epsilon 1 times x to be given by 0 epsilon times Q0 union 1 minus epsilon 1 times Q1. Okay, maybe I should put an extra parenthesis here. Okay, so the notation is slightly heavy, but basically what this is saying is the following. I want to kind of, so if this is my x times S1, and say these two circles are Q0, and the circle here is Q1. What I'd like my manifold W to be the following. So I want it to be sort of a product. So this is 0, 1 times x. So I want manifold Y, the W, to be a product of Q0 with a little interval over here, and the same thing over here. And then in the middle, between epsilon and 1 minus epsilon, it can do whatever it wants, as long as it's a manifold. I don't know, something like this maybe. Okay? So in particular, well, maybe I should also say that, I guess I need also to assume that the boundary of W is contained in the boundary of 0, 1 times x. Like W doesn't have a boundary piece like in the middle of the manifold somewhere. That's a usual assumption, but I guess it's good to write it down. So anyway, with those conditions, then in particular, we have that the boundary of W is equal to 1 times Q union minus 0 times Q0. Okay, so I have a copy of Q1 over here in 1 times x, and then I have a copy of Q0 in 0 times x, and it follows from this that's the boundary can only be in 0 times x and 1 times x, and because of this condition, it has to be exactly that. Okay, and also that W is transverse to the boundary of 0, 1 times x. I mean, that's kind of obvious because near the boundary, this is a product. So yeah, so it'll be transverse so to that. Okay? All right, so last time I basically used this as the definition of a cobordism. And why is that basically the same thing? So it's basically because of the implicit function theorem. As usual, almost, that's kind of the main theorem that we use in this whole class. I'm going to draw a picture, and I kind of will leave the details if you want to write this down. Maybe I'll say more than just the picture. I'll write a few more details, and if you want to write every line, you're welcome to. But basically, if you just assume these two conditions, what you have is that in principle, you start with something that's not cylindrical near the ends. So it's something that's just transverse. So if we just assume that, say, x, the w, well, if we just assume these conditions, let me call this star. If you just assume star, then what you have is, let me draw the picture. So say let's start with the 0 times x slice. Or actually, yeah, so you have something, so here's your Q0. And you know that W is transverse. So that means that when you project to W, to 0, 1, then you're gonna, the map is going to be, 0 is going to be a regular value of that map. So, you know, being transverse, W being transverse here, means that when you project from W to 0, 1, that 0 is going to be a regular value of this. So 0 is a regular value of pi. And the proof is, now the proof is very similar to the proof of what happens when you take a regular value of a function and of the boundary of the function. So basically now by the implicit function theorem, I guess one way to say this is by saying, well, by the implicit function theorem, then you can see this kind of as a graph from Q0 to a little interval, 0 epsilon if you want. So that's one way, and you can use that graph to move it, and you kind of extend it, and you can see that this is kind of the same as a product. That's one kind of approach. And another approach that's a little different, but actually is easier, maybe I should just keep one approach, is you can actually consider a vector field. So you can consider a vector field. So we can let, say, V be a vector field on W intersection with 0 epsilon. Sorry, you start, no. Yeah, W intersection with 0 epsilon times X. That's contained in it. So something like this. Okay? And you can think of this vector field really as a vector field that, so you can kind of think of this vector field as a time-dependent vector field on X. But actually not on all of X, but just on some little neighborhood of X, which is kind of the intersection of this W with each slice. And then you can extend this to a vector field on the whole of X, using where it's mostly 0. So kind of because So any vector field you can extend it if you're allowed to be 0 in some places, but actually I want to allow it to be 0 in most places. So you can kind of just take a little neighborhood of this, and you can use a bump function or something, and then to kind of kill it off. But I guess the set of vector fields is contractible anyway, so you can kind of always connect something if you allow them to be 0. So anyway, you can choose a vector field here, which I guess is the same as sort of an autonomous vector field, at least for t between 0 and epsilon. That's the same as a vector field on 0, 1 times x. But I want to construct it coming from a vector field here to make sure that the flow of this non-autonomous vector field is going to be contained in this guy. Okay? So once I do that, oi. Não, porque a gente normalmente para definir a vizinhança tabular, você precisa de um campo vetorial que é normal, que é transversal. E aqui eu quero um campo vetorial que é paralelo. Yeah. So, no, we want a vector field that's tangent. And that always exists because, actually, you really have to suppose that if you use this pi, that pi star of V is never 0. Because you want a vector field that will project to d dt, or projects to something with a factor of d dt. But if it's not d dt, so basically what I want to say is that this v is going to have the form d dt plus some other vector, some v tilde. And this v tilde really is a vector field, and it could be time dependent on x. Okay. And actually, I don't want this to be 0 outside of this neighborhood. I want vt tilde to be 0 potentially. But I want the other part, the part on ddt, to always actually be ddt. And if I start with something that projects down to something non-zero, it is the same direction. So we might as well assume that it's a positive multiple of ddt. And it can divide by, so if you start with something that's not ddt, then you can kind of replace this with v divided by dt of v. The one form dt. And this condition here being different from 0 is the same as saying that this thing is different from 0. So by doing this, you kind of make the factor in front of dt 1. So anyway, this is a kind of a differential geometry problem. So once you have this, and this vt is a globally defined vector field, and actually has compact support, then you can integrate this. And to be completely, to do kind of the same thing all at once, you probably want to do the same thing near 1, but using q1 instead. And basically, in the middle, you're going to have a vector field that's just ddt. Right? And you kind of know that the vector field is always, so your vector field is always ddt plus some other vector field on x that's autonomous, but whose flow, such that the flow of the whole thing is going to preserve this w here and here. Anyway, so then the flow of this vector field will actually give you a map that goes from 0, 1 times x to 0, 1 times x. And the point is that now, basically, if you take so you have your w here, and if you take the preimage of w, this is actually a diffeomorphism. So if you take the preimage of w, that will give you basically another cobordism. But now it's going to be cylindrical near the two ends. Because kind of by definition, if you take something cylindrical, if you take sort of 0 epsilon times q0, that's going to be inside of w. And the same thing for 0, 1 times 1 minus epsilon 1 times q1. So anyway, you have to check a few things. Like if you want to fill in, if you really want to write down all the words here, I encourage you to do that. But anyway, this is the idea. The proof is basically complete, but I think you can actually spell things out to convince yourself that this is true. Okay, so then this one will satisfy the definition. So this one is a cobordism as the definition above. Anyway, this is kind of a long detour just to tell you that you might as well assume that your cobordism is cylindrical. So it's kind of trivial near 0 and near 1. OK. Any questions about this? OK, so now let's look at the normal bundle. And as I told you, I'm kind of being really kind of careful here because I want everybody to understand what I'm doing. And I'm choosing a Riemannian metric. But I could actually not do that. But anyway, I'm going to keep choosing a Riemannian metric to talk about the normal bundle. So if G is a Riemannian metric, on X, then we're going to define a Riemannian metric on we're going to define G tilde, which is going to be a Riemannian metric on 0, 1 times x. And it's basically going to be sort of a trivial Riemannian metric that will make each cross-section orthogonal to 0, 1. So this is dt tensor dt plus g. Yeah. Okay, so clearly d dt is orthogonal to a slice t times x. Okay. So now, so if W is a cobordism, I guess let me say, let W be a cobordism from Q0 to Q1. And now I'm assuming it's a cylindrical cobordism. So that means that, well, first of all, I have a map from the boundary of W that goes into Q1, this joint union with minus Q0. So that's just a map that kind of forgets the T, because the boundary is Q1 times 1 and Q0 times 1. And I can, of course, take this to be an orientation preserving. I mean, this map that just forgets the T coordinate is an orientation preserving diffeomorphism. And the thing that's great is because of this condition, that means that ddt is going to be contained in a normal bundle of W. So if you take, so for each point, if I take a point, say 0x in the boundary of W, then the normal bundle, like that, of W, so this is going to be generated by ddt, and then something in the normal bundle of Q0, and then a basis of the normal bundle of Q0. Or actually, I should say like this. So the normal bundle is going to be given by R times ddt plus the normal bundle of Q0. Or maybe I should use this map, this phi, like under phi, there is a there's an identification here. Okay, because you're in the neighborhood of 0 epsilon, W is just a product. 0, because there you just have, then W is just 0 epsilon times Q0. So the tangent space is going to have this direction. No, sorry, this is wrong. All right, this is not what I wanted to say. Sorry. What I wanted to say was the tangent space of this guy is going to be the same as the tangent space of Q0 plus this direction ddt. Okay? So when I look at the normal bundle, there's actually going to be an identification of the normal bundle with just the normal bundle of this guy. Because of this condition here, because ddt is orthogonal to the fiber. Okay, so because of that, so maybe I should say that. So because of that, there is the normal bundle of W on 0 times Q0 is identified with, I guess, the pullback of the normal bundle of Q0. And the same thing for the normal bundle on 1 times Q1 is identified with the pullback of the normal bundle of Q1. Okay? Yeah. So anyway, I think it's kind of clear they have the same dimension, and the identification is kind of simple. I mean, this is kind of almost basically just a projection, like where you forget the T. And basically, if you are inside of this guy here, and you're orthogonal to everything in Q0, you basically just have to check that you're also orthogonal to DDT to be in the normal bundle of W. Okay, sorry there was slight confusion, but again, let me say one more time, like W in this neighborhood is going to be basically 0 epsilon times Q0, or epsilon 1 minus epsilon 1 times Q1. So the tangent space is going to be the tangent space of Q0, direct sum with what's spanned by DDT. Okay, and the same thing here. So anyway, so that's kind of what I wanted to say. So then that means the normal bundle of W, when restricted to the 0 and the 1 fiber, the 0 and the 1 sections, they are going to be exactly the normal bundle of the manifolds Q0 and Q1. So it makes sense now to say that a framing on Q0 and Q1 extends over the whole cobordism. So that now, or in other words, if I have a framing of W, then I get a framing of Q0 and a framing of Q1. So the conclusion is, a framing of W induces a framing of Q0 and Q1. Okay? By just restricting the framing to the two slices, 0 and 1, and using the isomorphism to bring it back to Q0 and Q1. Okay. So is that clear? I mean, if you want, I can draw the picture here, So sort of I'm thinking of my X. I can kind of draw the picture again. That I had. And you kind of see, in this picture, if my X is two-dimensional, then my framing is just going to be like a non-zero section. And it's pretty easy to see that, basically what you need is like a normal, on X, you need a normal vector field to your circles. And then when you extend it here, you need a normal vector field to the surface, to this pair of pants. So, if I just have to pick a non-zero vector field here, and that's a normal vector field here, that's non-zero, and that's going to extend to a normal vector field here and here. Okay. So in this case, it's very trivial. There's just two things you can do. There's not a lot of variety. But if you're in higher dimensions or in higher codimensions, then it would be a lot more interesting. Okay. Yeah, so basically if, I guess the definition would be then, so definition, so if Q0, eta 1, and Q0, eta 0, and Q1, eta 1 are framed submanifolds of X, a framed cobordism between them so it's a pair where W is a cobordism and eta is a framing on W that restricts to eta 0 and eta 1. So, well, let me write it like this. A framed cobordism between them is a pair, or is a framed manifold, is a framed submanifold W eta, where, so it's a W is a cobordism from Q0 to Q1, and sort of eta restricted to 0 times Q0 equals eta 0, and eta restricted to 1 times q1 equals eta 1 under this, kind of canonical identification given by this phi. Okay, so that's what a framed cobordism is. And it's not hard to see that, maybe I can kind of leave it as an exercise, that being framed cobordant is an equivalence relationship. So I guess, you say that two framed submanifolds are framed cobordant if there exists a framed cobordism. I guess I won't write that. It's kind of obvious. So the exercise is that being framed cobordant is an equivalence relation. So, basically, if you take a submanifold, a framed submanifold, you can take the product of the manifold with 0, 1, and keep kind of the same framing for every t, and that will be like sort of the identity framed cobordism. If you have a framed cobordism, you can reverse it, just changing t with 1 minus t, and then you have a framed cobordism in the opposite direction. And if you have two framed cobordisms, then you can compose them. You can just glue the two manifolds. And you have a framed cobordism, a glued framed cobordism. So you have transitivity. And it really helps here to actually have the cylindrical condition. Because if you have the cylindrical condition, then it's easy to glue. If you don't have the cylindrical condition, then it's a little harder to glue. And to be really, really precise, if you wanted to glue trivially, you would need this triviality condition in the little cylinder. But anyway, I kind of got tired of writing all of that. But you might want to say for every t sufficiently small, there is an identification here, and then you can say, okay, I want the cobordism, I want the framing to coincide not just at the slice, but in a little neighborhood, so that you can just really glue and say this is a smooth gluing. Because otherwise, you have two things, like you have a continuous gluing and you have to perturb it a little bit to make it a smooth gluing. Is that clear? You could kind of change this guy abruptly in some direction, like, and then you can change it abruptly in another direction. And then when you glue it together, it's not a smooth framing. So anyway, so you can assume the framing is cylindrical too, if you want. Okay, any questions about this? Okay, now I'm going to do an example with kind of all the details too, because I think it's good to understand everything that's going on. So oh yeah, no, I do have more than one example, so I can write the S example. So the first one is very nice. It's kind of, it has to do with kind of the degree. So I'm going to start with a, say I choose 3 points in X. So I have P1, P2, P3 in X. And I have Q in X. These are two dimension 0 submanifolds. And I want to orient these guys like this, plus, plus, minus, minus. And I want to show that basically, plus, plus, minus. And I want to show that these two submanifolds are framed cobordant. And again, like when I just put a plus here, something that you should kind of see is that if you choose the orientation of a point on a manifold, that gives you, and the manifold is oriented, that doesn't really give you a framing, it gives you an isotopic classes of framing, because that's what the orientation gives you. So it doesn't give you a specific basis, but it kind of gives you whether a basis is positive or not. So really a framed point is a little more than an oriented point. But sort of every kind of oriented point has a framing. It's just a choice of a positive basis. But so I'm kind of going to be a little blurry here. But because the actual framing will depend on the cobordism that I'll construct. But it's not hard to see that if you just have a point with a certain framing, you can just kind of turn the framing. So if you take two positive bases, you can connect them by a path, and that will be a framed cobordism. But anyway, let's do it like this. Actually, that was my second example, what I just said. Well, let me do the second example first so that this thing makes more sense. So anyway, sorry for going back and forth. But so let's say, because this is a higher kind of codimension in general, so let's say Q is a submanifold. And let's say that eta T is an isotopy of framings. So what does that mean? That means that for each, say that T is between 0 and 1. So that means that for each T, eta T is an actual framing. So it's a trivialization of the normal bundle. So then we can construct, basically the conclusion is that Q0, eta 0, is framed cobordant to Q1, eta 1. Okay? And why is that? Well, you can just look at your W to be, you define W to be, Q. So you just define your W to be 0, 1 times Q. Okay, and then kind of clearly, the normal bundle, because we chose the metric in that way, that DDT is orthogonal to each slice, so then the normal bundle at each slice, for any point, the normal bundle of Q at, say, I guess I can write it like this, the n of Tx of W can be canonically identified with the normal bundle of Q. So for every x in Q. Okay, that's because in W you have one extra direction which is orthogonal to nx. So then you have this identification. So that means that you can use eta t to be a framing for this normal bundle. So you kind of define eta to be sort of eta t on this n tx of Q for every x in Q. Okay? All right, so that's kind of like, if I guess you can think about drawing the picture, sort of if you have, here's your submanifold, you have this cylindrical cobordism, and then, if you had your submanifold, then if you have one framing, and then you have an isotopy, sort of you can use this 0, 1 to take this one framing and to kind of move it around to get to the end of the isotopy. So anyway, an isotopy of framings will induce a framed cobordism between the two, the framing, the submanifold with one framing and the submanifold with the other framing. Okay. So, that's, so in a way, like framed cobordism is kind of is a more general notion than just like an isotopy of framings on the same submanifold. Okay, so that's the first example. Are there any questions about this? So in particular, let's go back to the example that I really want to do, which is when you have some points. So I'm going to kind of do the simplest thing, which is I want to take 3 points on x, and then I want to take a separate point on x. I mean, you can assume they're all different. It doesn't actually matter that much. At least I want these three to be different. And I want to orient them like this, plus, plus, and minus. And this one is a plus. And by this first example, really up to a framed cobordism, it doesn't matter which exact framing I pick on the point. Because I want it to be compatible with the orientation. But if you fix an orientation, any two framings that are positive are equivalent because there's just two connected components of the set of bases, and they're given by orientation. So any two positive bases at a point can be oriented by a path. Okay? So I might as well kind of choose the exact framing that I want, the exact basis that I want later. So the pluses and minuses are enough. So in example 2, I'm gonna prove that these two these two framed manifolds, or at least these two oriented submanifolds, are framed cobordant. Yes? Não. Não precisa ser conexo. Nem a variedade X precisa ser conexa, na verdade. So yeah, so not even X needs to be connected. In fact, the only reason you assume X is connected in the Hopf degree theorem is for the degree to be an actual number. Because if you don't assume that X is connected, then you have kind of a degree on each connected component. Yeah, but sorry, here I'm going to assume that X is connected. Otherwise, that's what I'm just setting. What I just said is not true. I won't be able to connect the points. So here I do assume X connected. Because if X is disconnected, then these guys are not going to be frame cobordant in general, if I pick points in different connected components. But I just want to make sure that, really what I need, and you see, it's very easy to see why, is I want P1 and Q to be in the same connected component, and P2 and P3 to be in the same connected component. But anyway, I kind of already alluded to this last time. But I can kind of draw the picture. So what I want to do is the following. And maybe if you didn't understand the proof of Tom of the Hopf degree theorem, maybe it's going to be clearer now. But today, P1, P2, P3, and then here's your Q. So basically, what you want to define is the following cobordism. Yeah, but actually I prepared, and we can write down this explicitly. So how do you write this down explicitly? It's not very hard, but I think it's good if you feel like a little lost in this to see an explicit description. So you start with paths. So take paths, smooth paths. So first I want a gamma. So I want gamma and eta. Well, I was using eta for framing, so maybe gamma 1 and gamma 2. Gamma 1 and gamma 2. Gamma and sigma. Okay. Gamma and sigma from 0, 1 to x, such that, so I want gamma of t to be identically equal to P1 if t is between 0 and epsilon, and to be identically equal to Q if t is between 1 minus epsilon and 1. So I want a path that starts kind of stopped from 0 to epsilon, and then it moves around, and then it arrives to Q right before 1, and kind of stays there. And then the same thing, I want a path sigma, such that sigma of t is identically equal to P2 for t between 0 and epsilon, and P3 for t between 1 minus epsilon and 1. Okay. And then now you can define, so let gamma tilde of t be t gamma of t. And then I want sigma tilde. Okay, so this is easy. I just kind of take my path, And then as I move the position from P to Q, I just move T. And then for sigma, I want to go back and forth. So I'm going to put a quadratic function. So I'm going to do like T, 1 minus T, and then sigma T. Okay. All right. And now it's kind of clear to see that, that behavior. So now I just, I can let W be the image of these two maps. So the image of 0, 1 union the image of 0, 1. To make it simpler, I can kind of assume that these paths don't cross. But if they did cross, then it's actually not so hard. It can kind of perturb them a little bit so that they don't cross. If they cross, the only time this would be a little complicated, yeah, it would be if x has dimension 1. But yeah, but I guess if you want, you can assume x is higher dimension. But anyway, if x has dimension 1, you have to be a little bit more careful about which points you connect. But anyway, let's not be too worried about that. I think you can kind of visualize what I'm saying. By transversality, you can suppose that these two parts don't intersect. So this is really an embedded manifold. So this is a cobordism from, let's call this Q0 and Q1. Q0 and Q1. Q1. Okay, so now the one thing I do want to say is that, and maybe it's not completely obvious, is that there is a framing. You can choose a framing here that's going to give you exactly the framings, these two framings, and there's going to be another framing here that's going to give you exactly these two framings. So how do you see that? Basically what you have to see is that there is a way to kind of choose a framing on this normal bundle that's going to agree with the framing here and here, and the same thing here. Okay, that this cobordism can be framed. I mean, looking at this picture, it kind of, at least here, it looks kind of obvious. This one, maybe not so much. And I kind of said this last time on the proof of the Hopf degree theorem. Maybe some of you looked at me like, I don't quite understand. So let me actually write out all the details of that. So how do you frame this cobordism? So what we need is first of all, we kind of need to show that. So for the first part, so for the gamma tilde, so let's frame gamma tilde first. That's the easier part. So what is the normal bundle of gamma tilde? So what is the normal bundle of gamma? So I'm going to think of W as being the union of gamma tilde with sigma tilde. So it's a disjoint union, so I can frame each of them independently. Okay, and I'm of course identifying the path itself with the function, with the parameterization. Okay, so what's at gamma tilde? If I'm normal to gamma tilde, then that means I'm normal to the derivative of gamma tilde. So that just means, so what is a vector here? So let me write it like this. So a vector field, so something ddt plus v. So this is a vector field on t of 0, 1 times x. So let's say this is tx. Okay? So the first part is something ddt, a multiple of dt, and the second part, v, I'm thinking of v as being a tangent vector to x. So this is something in the normal bundle gamma tilde, if and only if, when I take the product with the tangent vector there, then I get 0. So what's the tangent vector there? So this is going to be sort of A gamma A dt plus V, and then inner product with d dt plus gamma prime of t. Okay, because gamma tilde of t has this description. Okay, so this has to be 0. So this is if and only if A is equal to minus V gamma tilde. So there we go. Okay, so that means, if I want a certain V, I can always choose the A so that I actually am taken to the normal bundle. So that means that, because of that, there is an easy identification between the tangent space of X and the normal bundle of gamma tilde for every t. That just takes a vector V and brings it to minus V gamma tilde ddt plus V. Okay, so what does that mean? Sort of if I have this path here, so near 0 and near 1, it's cylindrical. So my gamma is constant, so gamma prime is going to be 0. I'm just going to go V goes to V. So I have the kind of trivial isomorphism under the trivial identification. And then as I kind of move along, then I can't just keep that tangent space, the tangent space to X, because that's not going to be normal to the curve anymore. I might have to do something like this, depending on where I am. But anyway, this is an isomorphism. This is an isomorphism. So that means if I choose a specific basis here, if I just choose one basis that I like of this guy, then I can frame the whole curve. And in particular, I have my fixed framing of P1 and of Q. I can use that to choose a framing of P1 and Q, and that I can connect by another framed cobordism to whatever one I want. Okay, so that's easy. So that's kind of that's the gamma tilde part. Okay, so what about the sigma tilde? It's a little bit trickier. And you see why. Do you see why? Well, you see that the problem is that here we don't have t anymore. We have this kind of other function of t. So that function is going to come in here. And if that function is 0, so exactly at one point when you kind of are turning, then you have a problem. And you should have a problem, really, because you're like flipping things around. Okay? So how do you deal with that? Well, it's kind of a calculus problem in a way, but maybe something from the problem set, but I think it's worth writing it down. So now sort of the tangent space to W at a point sigma tilde of t. So this is now spanned by what vector field? So 1 minus 2t times d dt plus sigma tilde of t. And to make things, kind of easy, a little easier to write down, I can assume that sigma t is different from 0 near for t 1/2. So we can assume that, or sigma prime of 1/2 is different from 0. so that we actually have something that doesn't vanish there. Because exactly the point t equals 1/2, this path really, as I defined, it comes all the way to 1/2 and comes back. So I assume that. Okay, so what is the normal bundle? So basically, now if I have something that is on the normal bundle, just sigma tilde, then I can write the following thing. So the normal bundle. So you see, this is a little more complicated now, because when this is 0, then dt is no longer in the tangent bundle. So sort of dt will be in the normal bundle now. So that's why you can't have an identification that's as simple as that. So now basically, let's write it like this. So I want a map that will go from the tangent space to the normal bundle of sigma of t of w, of sigma tilde. Okay, so if I take I can look at a vector in the following way. So I can think of a vector as, so I have my part d dt, and then I have a part that is tangent to gamma t, gamma prime of t, and then I have a part that is perpendicular to gamma t. So something like this. So this, I'm assuming for now that gamma prime is different from 0. Okay, so I just don't want to spit out a formula. I mean, I have the formula written down, but I kind of want to explain how you get to the formula so you don't think it's magic. But anyway, so if I have something of this form, and I want the product with this guy to be 0, then maybe I should say, I can call this sort of, well, let's just leave it like this. So the condition that you need is basically, well, I don't need a C here, because V is just something that is perpendicular to gamma prime t. Okay, so then when you do the inner product, you get that a times 1 minus 2t plus b times the norm of sigma t. Well, you can, this is equal to 0. Okay, so what that's saying is that basically, as long as this guy is different from 0, then I can find something here and something here that will make this guy 0. So actually, given an A here, I can find a B to make it 0. Or vice versa. Given a B here, I can find an A here, so that this is 0. Okay, so basically, I can think of it the following way. So I can think of it like this. So again, this is still the sketch. So if I have something of the form A eta prime of t plus v, where v is something in eta prime perpendicular, I can take this to v and then minus b d dt, and then plus b times 1 minus 2t over the norm of eta t square. So that's kind of, oh, sorry, not b, a. So that's kind of what you get from the calculation I just did. That any vector of this form, there is an easy way to take it to something in the normal bundle by just doing this. Okay? Wait. No, times, no, not eta. I keep saying eta. It's sigma. That's, again, what happens when you write something on your notes and then you change it in the class. So I don't recommend that. You should apologize to the students that have something that has a problem. So anyway, times sigma tilde. Okay, so this is kind of what I want to do. Okay, and the reason I want to do it this way, maybe I guess you could do it a little differently, and you can kind of expand v or something. Like you can multiply everything by the norm of sigma tilde of sigma prime squared or something. But first of all, this is going to work, and at least when gamma tilde is different from 0. So this works when sigma tilde of t is different from 0. Okay, when sigma tilde is 0, then it doesn't quite work. But then basically, or I guess, what you can do is you can write down a formula that will always work. I guess, yeah, so maybe I can tell you the formula right now. Yeah, so here's the formula. Maybe you really actually do. Maybe you do want to multiply this by sigma tilde squared. Anyway, that was. But still, this doesn't quite work, because for this to work, you need to be able to have a decomposition like that. And this decomposition doesn't exist when sigma tilde is 0. But anyway, you can kind of extend this continuously to the points where sigma tilde is 0. But I mean, I guess at this point, I'm just kind of doing something trivial in front of you, or some kind of trivial linear algebra. But I guess you can write the following things. So you can write the map that goes from sigma t of x into the normal bundle of sigma tilde of sigma tilde that will take v. I guess what you can do is first you can take this to sigma tilde squared times, and then now I'm going to do the following thing. I'm going to do v minus. Yes, I'm going to project. Anyway, I have this expression. I think it's kind of pointless to write this down at this point. But anyway, I think, yeah, I'm not going to write this down. It's not a calculus class. But anyway, so once you have this, I guess now, basically have to see that this can be extended also to the points where sigma t is 0. Sigma t prime is 0. And it's not hard to see that this can actually be done. Okay. So, actually, okay, sorry, you don't actually want to multiply by this. Okay, sorry, I should have prepared it slightly better, but anyway, I think that maybe it's more pedagogical now to let you finish this. I don't want to multiply by that, because then that would actually mean that when sigma prime is 0, then I go to ddt, which is not true. So I really want to go to this. So maybe what you want to do is you want to keep the v. Oh, yeah, I think I do have it here. Yes. Oh, yeah. OK, here was the expression that I had. So kind of first, what you do is you project it. You take your vector in x, and you look at the projection to the sigma tilde, to this thing, and you pick up this a using some orthogonal projection, and you plug it in here, and you kind of have the rest go to the identity. Okay, and then you kind of show that in the case when this guy is 0, then that formula is still fine. The formula is still continuous. Okay, so anyway, if you take this expression here, and you try to rewrite it instead of having a sigma tilde, just using orthogonal projections or something, you'll see that you can actually extend this smoothly to the case when sigma prime is equal to 0. But it's kind of, when you look at the picture, it's kind of easy because the part where sigma prime is equal to 0 is the easy part. So it's kind of the cylindrical part. Sort of the part when this guy, like for example, when here it's equal to 0, that's kind of the easy part when you just have v goes to v. Okay, so you're really not projecting on anything. So yeah, so there we go. That's kind of what I wanted to say about this. So anyway, at the end of the day, what is this doing? This is giving you a map. This is telling you that if you choose a framing here, then you can frame this guy. And what's actually nice is you should just look at one thing here, which is kind of what is happening with the orientation here. So what's happening with the orientation is, if you think kind of carefully about what's happening, is that if you start with something like a sigma tilde plus v, then kind of when you come back, you have the same v, but the sigma tilde has a factor in front. And this factor has a positive or negative sign depending on whether t is close to 0 or close to 1. Okay, so when t is close to 0, this guy has a plus sign, it has a minus sign, and when t is close to 1, this guy has a minus sign, which is consistent with kind of what you had. So you had a path that goes like this, and it starts from plus and it ends in minus. And you see, that when t equals 0, you actually start in plus. So this has the same orientation. So you kind of have the same positive guy with sigma prime and v. And then you end here, you end with a minus. Okay. And I should be, there are a lot of little subtleties, which is like, actually for this guy, for this particular calculation that I wrote down, you probably don't want the thing to be cylindrical. So it actually would be easier if it's not cylindrical. So it would actually be easier if you start moving the point right away. And then you wouldn't have the problem that this guy is actually, this derivative is 0. But anyway, I kind of told you it doesn't really matter if you start kind of constant or if you start moving right away. And you can kind of look at the first place when it moves, and then you have this property that I'm saying. So, kind of you have one vector here, and then you have the whole other space. And, basically what this is saying, this isomorphism is giving is like, for the rest of the space, you keep it constant. And for this one direction that's, given by this derivative, you start with something positive, and then you end with something negative. So that's why you kind of start with an orientation that matches the original orientation, and you end with an orientation that flips the original orientation. Okay? So anyway, that's it. I'm sorry, I maybe should have prepared a better formula, but I think it is a good exercise for you to finish juicing the orange. Okay, so with that said, now we can actually state the Pontragon Tom construction and prove that it works. Okay, so remember, basically that, recall that if X, is a compact oriented manifold with no boundary, and you have a function from X to Sm, and A is a regular value, so F is transverse to A, then the preimage is, then I explained to you last time that the preimage is a submanifold that admits a framing. So the preimage inherits a framing. And how is this framing chosen? Well, I explained to you, that the derivative, if you take a point in this preimage, then the derivative of f gives you an isomorphism from the tangent bundle, from the normal bundle, to the tangent bundle of Sm. So now if you choose, so this is an isomorphism, So if now you fix a basis here, and you take the preimage of this basis, that will give you a basis at every point x. Okay, so that's the framing. And now, if you actually change the basis here by a, if you change it to another oriented basis, I mean, you fix your orientation of SM. Otherwise, that's not going to be canonical. But if the SM is, is canonically oriented, and you fix another basis that's positive, then there's going to be a path, an isotopy of bases, and that's going to give you an isotopy of framings. And I showed you, a little bit earlier that if you have an isotopy of framings, then you have a framed cobordism between sort of one and the other. Okay, so, but anyway, it's even more. So, but basically what happens is, so I guess, yeah. So the theorem is that there's a map that takes smooth functions. So this map, so from a smooth function, I actually get a framed submanifold of X of codimension M. So kind of, I kind of told you how to do this, but there are some choices here. And anyway, if I actually mod this out by homotopy, and here I mod this out by framed cobordism, framed cobordisms, this map is a bijection. Okay? And it won't even matter. It won't matter which regular value I choose, and it won't matter which specific basis of SM I choose. I will just, really have a bijection. So this will tell you that classifying maps into SM up to homotopy is the same as looking at framed submanifolds of X of the right codimension up to framed cobordisms. And I think I convinced you, hopefully, by the previous example, that in the case when X is connected and the dimensions are the same, a framed submanifold of X of codimension of the dimension of X is just a bunch of points. I think I convinced you with the picture earlier that this set up to framed cobordisms is the same as a degree. That's kind of what my example is trying to convey. And I explained this last time with the pluses and minuses, like kind of line up all the pluses, you line up all the minuses, and then you end up with the same number of pluses or minuses on one side or the other side. Okay, so that's why this is a generalization of the Hopf degree theorem. But of course, this is much, much more general. But surprisingly, the proof is going to be the same. So the proof that I'm going to give you to this theorem, or the hardest thing here is to understand what the theorem is saying. But the proof is going to be almost the same proof as the proof of the Hopf degree theorem from last time. Okay. But if anything, I think this language makes it clearer. So I'm going to start with step 0, which is I kind of already said, but I want to write this down, which is that it doesn't matter which basis of SM you choose. So I guess the first part is, so suppose we have the function like this. So, suppose we have a function f. A regular value. Then the framing or the framed manifold or sorry, the framings do I say this? The framed, no, the framings on the preimage of A by F induced by two different positive bases of TA of Sm are isotopic. Okay, and therefore, I guess, therefore, the induced framed submanifolds are framed cobordant. Okay? I mean, I kind of already said this in words, but kind of let me say this one more time, I'm saying, you have this submanifold. How do you get a framing here? You take a basis here, and you look at the preimage under the derivative. So if I take two different bases, if they're both positive, then that will imply that I actually have an isotopy of bases that connects one to the other. Okay, that's a simple fact from linear algebra. So if I take the preimage of the whole isotopy of bases, I'm going to have an isotopy of framings of this fixed manifold, F inverse of A. And then by the first example that I gave of framed cobordisms, that's going to give you a framed cobordism of the inverse image of A with one of the framings with the other one. And that's it. Okay, so that's step 0. Any questions about this? Okay. So step 1, I guess it's kind of in a way, it's the first real step, is what happens when I change the homotypic class? So I kind of have to say a few things. Like I'm going to say this really doesn't depend on choices. So first of all, what happens when I change the homotypic class? And then later I'm going to tell you what happens when I change the regular value. Okay, so step 1 is the homotypic class. I forget if I already said this last time, but maybe I did. So step 1. So suppose F is homotopic to G. And let's say that let H be a homotopy. So, of course, F and G are smooth functions from X to Sm. So define the homotopy, and I didn't tell you that you can change A, but if you bear with me for a second, let's just take a regular value for both of them. Let's say that there exists a regular value for one of them, and then you have one submanifold, and then there exists another value for both of them for the other one. But I actually want to start by taking a regular value for the whole homotopy. Okay, so I can let A be a regular value of F, G, and H. And as I've explained before, you could have just start with a regular value for F and G at the same time and pick an H and perturb your H so that A is still a regular value for H. Or sorry, so that A is a regular value for this new H. And it's still a regular value for F and G. Anyway, and F and G, of course, are what we call the boundary of H. So now we can define, so we can let W be H inverse of A. And again, kind of using the same construction here, and something else, to be kind of very precise, you could assume that H is constant near 1 and near 0. So instead of taking a homotopy that just kind of takes F directly to G, you can say, I'm going to start by being kind of fixed. I'm going to stop at f between 0 and epsilon. Then I'm going to move to g. And I'm going to arrive at g at 1 minus epsilon. And then I'm going to be stopped at g for between 1 minus epsilon and 1. To have really a cylindrical thing. So if you have this condition, then this guy is really, so let this guy, then this w is a cobordism. From F inverse of A to G inverse of A. And moreover, we can frame W in the same way. Kind of exactly the same way. We can use DH X to frame W. So that goes from the normal bundle to TA of SM. And we pick a basis here, and that's an isomorphism. So that, that gives the framing of W. And because, when you restrict H to 0, you get F. And when you restrict H to 1, you get G. That means that you actually get exactly the framings that we got from F and from G. So therefore, F inverse and G inverse of A are actually framed cobordant. Okay, and this, is giving you the framed cobordism. Okay? I mean, of course, when you restrict, maybe that's not completely obvious, but it is true that when you restrict DHX to the fiber, 0 to the slice 0 times x, you get exactly DF. And the same thing at the other slice, you get DG. That's why you get exactly, when you restrict this framing to the two slices, you get the framing on F inverse of A and on G inverse of A that you chose from a fixed basis here. Okay. And notice I'm not really choosing any kind of global section of this tangent bundle. I just take one tangent space and I fix a basis. I'm not moving the A around. I just have a fixed A. Okay? So I'm not using any idea about triviality of tangent bundles of spheres, nothing like that. It's not true in general. I'm just taking one vector space which has a basis. Okay? And then I move it around just in the normal bundle of the preimage of A. Okay, so that's step 1. So step 2 is what happens when I change the regular values. So given, so let A and B be irregular values of F. So I want to prove that that F inverse of A and F inverse of B are cobordant. Okay, so how do I do that? Well, I'm going to actually use a homotopy. And you see exactly how I do this. So basically, I can let psi t, well, I can find a diffeomorphism. Well, actually, I can find a flow that goes from Sm to Sm be a flow such that psi 1 of A is equal to B. Okay, by a flow, I just mean a homotopy of diffeomorphisms such that psi 0 is the identity. So this is, if you want, you can choose a vector field that does that. It's I don't know, there are many ways to do that. You can just take your A and B, and you can take a path, and then you can take sort of the derivative of the path, and you extend it to a vector field in the whole sphere that has mostly 0. And then you see how much time it takes to go from A to B, and you divide by that time, and then you get this for time 1. That's one way to do it. Okay. But anyway, so you can have something, and then you integrate, and that gives you the flow. So by flow I mean phi psi 0 is the identity, and this is a diffeomorphism. Okay. So now you can define. So basically psi t composed with f. This is a homotopy. So for t between 0 and 1, so this is a homotopy from f to phi 1 composed with f. And basically the preimage of so phi 1 composed with f inverse of b is equal to f inverse, phi 1 inverse of b. No, that's right, it's equal to f inverse of a. Which means that b is a regular value of this guy. Because they assume that a is a regular value of f. Okay, and this flow is a diffeomorphism, so it won't affect the derivative will be bijective. So because of this simple fact, because psi 1 of a goes to b, psi 1 takes a to b, then b is a regular value of psi 1 composed with f, and it's also a regular value of f. And because these two are homotopic, I proved in step 1 that if you take a regular value for the two things, then the both preimages are going to be framed cobordant. Okay? And you choose your homotopy. You might have to perturb the homotopy so that b is a regular value always. But you can do that with transversality theory. So hence, this preimage of b, which actually is f inverse of a, and f inverse of b are framed cobordant. Okay. All right, so that's step 2. So it doesn't matter which preimage you pick. Okay, so now I'm going to show that this phi is surjective and that it's injective. So now I'm going to first show that it's surjective. So I will pick a framed submanifold of x of the right codimension, and I have to tell you how to build a smooth function so that this preimage is going to be exactly what we want. Okay? So that is step 3. So you can think of this as kind of similar to, if you have codimensions, a total codimension, then, I guess if you have codimension 0 between the two sides, x and Sm, then your preimages are points. So this would be like showing that every degree can be attained by a map. Okay, so which is kind of an exercise that maybe you should have already thought about, but I guess I didn't quite ask you to do that. But if you understand this, I think you'll understand how to build a degree of any map. It's kind of the same thing. So step 3 is to show that phi is surjective. Okay, so we've already shown it's well-defined. I guess step 1 was to show it's well-defined. And I guess in step 2, we show a little more, and it actually doesn't matter which regular value we pick. And now we're going to see it's surjective. So we pick, so let W eta be a framed cobordism. No, not cobordism, a framed submanifold Why W? Oh, sorry, this is confusing. I'm going to do Q. A framed submanifold of X. And when I say framed submanifold, I mean oriented as well. So I'm always kind of, maybe I should say framed oriented submanifold of X of codimension of the right codimension. So of codimension M. So, that means that there is a isomorphism, a chosen isomorphism between the normal bundle and Q times Rm. Okay, so because if it has codimension M, then the dimension is N minus M, and then the normal bundle has fibers of dimension M. Okay? So now I use a very nice thing, so and basically now I obtain, so then we obtain an embedding that I'm going to call, well, I'm going to use this psi. It has nothing to do with this previous flow. So this is going to be, I'm going to embed Q times Rm into my manifold X such that psi of W of Q0 is equal to Q for every Q in Q. And moreover, when I look at the derivatives with respect to sort of U1 and UM, at a point x0, that is the framing eta x. So, kind of the way you can do this is using the exponential map in Riemannian geometry. I haven't exactly told you, proven the existence of the exponential map. But I think, it's not very hard to imagine. So I have this Q, and I have the normal bundle. So if I take a basis of the normal bundle, then what I can do is I can basically use the exponential map to find an embedding of sort of a Rm inside of here. And it is a theorem. It's a non-trivial theorem of Riemannian geometry. Kind of that the existence of geodesics. They can do that so that the derivative at 0, where you start, is exactly that vector that you start with. So you can use sort of your basis at each point to define this embedding of this Rm in a way that they won't intersect, and that this whole thing here is actually smooth. Okay, so yeah, if you haven't taken Riemannian geometry before, maybe this is kind of crazy, but it is true. You can do that. And there's another subtle point, which is that in general, if you want a geodesic, you only be able to do it for a little time. You can't do it like for all of Rm. But you have a maximum radius. So you can kind of use this maximum radius, which, because Q is compact, you really don't really even need that. But yeah, you don't really need this in general. But like if Q is compact, then you actually have a smallest radius, right? You have a minimum. So you can actually kind of rescale and take the whole Rm into that ball. And then I guess you have a new basis that's just equivalent to the original one using a factor. But anyway, I guess it's not so hard to see, at least that you can embed Q times a ball in here. But you can actually do this for the whole Rm using a diffeomorphism of Rm to a small open ball. Okay? So anyway, that's it. So as I said, there's a subtlety that maybe, if you shrink your Rm by some constant to make sure it fits in a geodesic ball, then you might, get a factor here when you choose the basis. But the basis is chosen up to isotopy, so you can always shrink each element of each vector of the basis by whatever factor you want as long as it's positive. Okay. So anyway, we have this embedding. And then now we're going to kind of do the same thing as last time. We just use the identity and the stereographic projection to define the function. So, you know, kind of, you think of your Q here, and then you have this tubular neighborhood. But the tubular neighborhood is a diffeomorphism with a trivial product. And then the idea is that the function is just, you just take it to the projection to Rm. So you kind of forget where you are in Q, you just take it to Rm, and then use the stereographic projection to take that to Sm, and you close up with a point. So now you let phi be the map from Sm minus, I don't know, the south pole into Rm be the stereographic projection and you know it's orientation preserving, and you can define f from x to m to Sm by the following formula. So f of x is equal to, so it's phi inverse of u if x is in the image of psi qu. And it's going to be the south pole otherwise. So if you're not in the image of this guy. So basically, you know, you have a punctured sphere for each of these guys here, and then the rest you just take to the south pole. Okay? So so it's easy to see that the North Pole, which is going to be exactly what happens when u is 0, so this is a regular value of f, and the preimage of this point is exactly equal to q. Moreover, and since the stereographic projection preserves orientation, basically you can just pick, you know, we can choose and basically, you know, kind of this embedding will give you what this embedding is saying is like, you know, when you project that to Rm, sort of this basis is kind of constant in Rm. So your framing, you know, which is kind of a basis that's changing, when you kind of pull it back here, then but this equation here, what it's saying is that when you pull back the framing to q times Rm on the 0 section, that is going to be like the Euclidean basis of Rm. So you can take the Euclidean basis of Rm to Sm, and then you have that a fixed basis of the tangent space to Sm on the North Pole. So, you know, so basically, so this guy preserves orientation. So, you know, kind of that means that when you take psi star of, or psi inverse, no, psi star, no, I guess it's psi inverse star of sort of the Euclidean basis of Rm. So this is a basis of basis of the tangent space of 0, 0, 0, 1 of Sm, and that's going to induce exactly the framing that we chose. So this induces eta on Q by, the function df. Okay, this is exactly because of this condition here. When you look at psi inverse, or I guess when you look at the push forward of psi inverse, this condition here just means that the framing, when you push it back here, that's going to give you always the elements of the canonical basis of Rm, no matter which point you are in Q. That's kind of why you chose this embedding. So that this framing that kind of varies from point to point actually is represented by just the constant framing in Rm. So that means when you look at it in Sm, it's just a constant framing in Sm with the right orientation. So there we go. That shows that it's surjective. So that shows that I can build a map so that the preimage of a regular value is Q, and it comes with the framing that I want. Okay, so that's step 3. So now step 4. I have to show it's injective. So step 4. Phi is injective. And interestingly enough, it's not much harder to show it's injective than to show it's surjective. And actually, we use the proof that it's surjective in a way to show that it's injective, which is kind of fun. So how do we show it's injective? So suppose you have two functions, two smooth functions. And suppose that A and B are regular values. Well, actually, we might as well assume it's just one A by step 2. So let A be a regular value of f and g, such that the preimage of A, so f inverse of A and g inverse of A are framed cobordant. I guess, first you start with a different B, but then I told you, by step 2, you can assume they're the same, so we can assume this. And when I write f inverse of A and g inverse of A, I mean, the submanifolds with the framing that's induced by, the map. So what we need to show is we need to show that f is homotopic to g. Okay, so how do we do that? So first of all, we know that they are framed cobordant. Okay, so this is the hypothesis. So we can let W inside of 0, 1 times x be a framed cobordism from f inverse of A to g inverse of A. Okay, so the thing that's cool is I can actually do the same thing here, and using this framed cobordism, I also obtain an embedding. Okay? So now we have, there is an embedding, there is an induced embedding from the frame cobordism that goes from W times Rm into 0, 1 times x. That's just thickening W using the framed, using the framing on the framed cobordism. And of course, it has the same properties. Like at 0, we are at W, and the derivative at 0, it kind of takes the Euclidean basis here. So, I guess this of x0 is x on W. I guess that's obvious. And I guess, phi star of EI, the Euclidean basis, is equal to exactly the framing. So on x0 is equal to the framing. On x. Okay. All right, so now what do we do? Well, we do the same game. We do the exact same thing. So, basically this, basically using the exact same technique, what we get is we get an actual homotopy of two maps into SM. So, you kind of, so here is your W. So you thicken it, and so it's a little harder to draw. I don't have enough dimensions, but kind of, so for each sort of fiber, so for each point on W, on top you have this little Rm. So you take the map that takes that Rm to Rm, and then you collapse it using the stereographic projection. So that means, you kind of obtain, so using this, you obtain a map from 0, 1 times x to Sm. And the thing that is interesting about this map is, when you look at the pre-image of the North Pole, restricted to here, well, so first of all, so you have this map, and then the properties that the pre-image of the North Pole is exactly equal to W. But then now you look at these two slices, the 0 and the 1 slice. And that's not really F and G anymore, but it has the same pre-image of 0, 1. So that's that's the next point. So the next point is, I constructed this homotopy, but it's not a homotopy from F to G. So if you call F tilde this F of 0 dot and G tilde F of 1 dot, the point is that F tilde and F are different, but they have the same pre-image of the North Pole. Or, sorry, not the North Pole, A. Oh, yeah. Yeah, so sorry, I use A to Here, I actually have to use the A that I already had before. Okay, so I use the stereographic projection with respect to minus A. So it's kind of what we did last time. So the stereographic projection with respect to minus A, we'll take this guy to, so this is Rm, and my phi will do this, and then I use my phi to map this Rm to the sphere, and then I have the property that the pre-image of A is W, and then I do this, and then the point is that, now when I look at F tilde inverse of A and G tilde inverse of A, I get exactly the same thing as F inverse of A and G inverse of A. Kind of by construction, because W was the cobordism between these two. Okay? And even more, this is true even with the framings. So this is true as framed submanifolds. Okay, so it's very similar to what we did last time. We wanted to show that F and G were homotopic. Using the pre-images, we built a homotopy, but it's not a homotopy between F and G. It's a homotopy between F tilde and G tilde. And F tilde and F, and now we basically have to show, so we need to show that F is homotopic to F tilde, and that G is homotopic to G tilde. And believe it or not, the proof is exactly the same as last time. Last time was just this proof for the case of codimension 0. So how do you do it now? Well, what do you know about f and f tilde? I'm just going to do it for f and f tilde, and it's the same for g and g tilde. You know that f and f tilde are two submanifolds. Sorry, you know that f and f tilde are two functions from x to Sm that have the property that A is the regular value for both, and the preimages are the same with framings, framed. So this is enough to conclude that they are actually homotopic. And you do it by hand. And you do it by hand kind of using like a linear homotopy in the stereographic projection. So we're kind of running out of time, and it's exactly the same thing that I wrote last time. So instead of writing a bunch of formulas, I'm going to kind of draw the picture. So, kind of what you know is that, so you have this submanifold. Let me call this Q. This is equal to this submanifold. So F inverse of A, which is the same as F tilde inverse of A. So here's my Q. So how do I construct a homotopy? So first of all, I look in a neighborhood of it, in a frame. So I know the framings are the same. So I have this, this embedding of Q times Rm inside of X. So this is my embedding, just like the previous step, which is actually a restriction of this embedding here, just to the boundary. But now I'm kind of forgetting the middle. I just want to look at the boundary. And then in this, if I look at this embedding, basically what happens is that because the framings are the same, so using the framing, after you precompose with this embedding, I guess. So when you look at F, compose with phi inverse, and when you look at F tilde, compose with psi inverse, this map, when you compose with the stereographic projection, will have derivative of the identity. So this will be a map from Rm to Rm with the derivative equal to the identity at 0, which stems from this condition here. And the way that you choose the stereographic projection to kind of, you can choose it so that it's the identity, so that the derivative is the identity at sort of the opposite pole to where you're doing the stereographic projection. So, the derivative here is the identity, which means that, both of these guys, you can write both of them, F and F tilde, as something like Z plus O, X. So this is X plus O of X squared. So you have that property that when you take the inner product with X, this is going to be positive. So, it's exactly the same thing. So this, when you take the inner product with X, this is going to be positive if the norm of X is small enough and different from 0. So this is true if the norm of X is small enough and not 0. So now, what you can do is in this little ball, you can look at a linear homotopy from F to F tilde. And then you use a bump function to make sure that it doesn't move outside of this ball. Okay, so, and you need this condition really here to show that outside of the 0, the origin, you're not changing, you're not going through anything that goes through the origin. So through the whole homotopy, the only points that are taken to 0, which correspond to A, are exactly the same point. So you're still on the same submanifold. So you find a homotopy that will go from, say, F to something else. So you find a homotopy from F to F double tilde. Or I think we did it the other way. We did a homotopy from F tilde to F double tilde, such that in this little neighborhood, it coincides with F. And then now you have to do a homotopy outside of these neighborhoods. And that's kind of easier, because now you use the opposite, the opposite stereographic projection about the opposite point, and then you just do a linear thing and you don't even need a bump function. Okay, so I mean, the formula is exactly the same from the Hopf degree theorem, the proof that I presented last time. So anyway, I think I'm gonna stop here, and then I think it's actually, I'm not gonna come back to this thing. So if you, I encourage you to think about this today, and then tomorrow if you have a question, or you know, we can talk about this. But yeah, so anyway, that's the end of the proof, and I'm gonna stop here. Okay. Alguma outra pergunta? Any other questions? No. Okay. Até amanhã. See you tomorrow.